unmute. So welcome everyone joining us online as well. My name is Hannah. I'm a PhD candidate here at the Trottier Space Institute, and I'm your moderator for tonight. And I'm also the TSI outreach coordinator. So I love spending time with all of you talking about science. So tonight we'll be learning about life out in the universe from some of the astrobiology experts here at the TSI. So before we get started, I just want to bring up a few reminders. The first is just that this is our code of conduct. So at the Trottier Space Institute, we're committed to providing science education to everyone in a positive environment. And to that end, we just want to make sure that everyone sees this. So if anyone at any point tonight has any comments, concerns, scientific or otherwise, please let any of us know who are wearing the Ask Me, I'm an Astronomer pin. We're here to help make this night really fun. So tonight, it's my pleasure to welcome our speakers, Brady O'Connor, Sam McNichol, and Aaron Gibbons. All three of our speakers are active researchers and PhD candidates here at the Trottier Space Institute. And tonight we'll learn about the Mars 2020 mission, how we can use Earth's extreme environments to help us learn about what life might be like on other planets and more. So after the talks, I'll ask you to just refrain from questions during the talks, but afterwards we'll have a question and answer period where you can ask our astrobiology experts your most pressing questions about life and other things. So for those of you joining us on YouTube, you can just write your questions in the chat and we'll get to those as well. So without further delay, oh, wait, one more thing. If you want to enter to win an MSI mug and hat, which, as I said at our last talk, if you were there, are very rare now because we renamed our institute to Trottier Space Institute. So these MSI mugs are, very rare now. Vintage find, as you can see. So you can scan this QR code, or if you had filled out one of those little papers earlier, you'll also be entered. So first up, we have Brady. Welcome.
Anna. Okay, so just like use this, but go based on that. Okay, hello everybody. So my name is Brady O'Connor. I'm a PhD student here at McGill University. And generally what I study is astrobiology. And just in case you guys don't know what astrobiology is, it is the study of life within our universe or the search for that life. But one of the issues with the whole study of astrobiology is it's really hard to do, right? Because in order to do it properly, you actually need to go elsewhere in the universe to collect samples. So as you might be able to understand, I can't just go to Mars tomorrow and grab a bunch of soil and look for life in it. So we have to rely on robotic spacecraft. But again, what you might be able to imagine is what we can put on a rover in terms of instrumentation is not as good as what we can do in our labs here on Earth. So basically what I'm trying to say is that we can't study life elsewhere in the universe as well as we could here on Earth. So we have to get creative as scientists in determining how we can study what life might be like elsewhere in the universe. So one of the ways that we do that is using Earth's most extreme environments. And what these are actually called is analog environments. So an analog environment is a place on Earth with assumed past or present geological, environmental, or biological conditions of a celestial body. So basically what that means is an analog environment is an environment on Earth that mimics some part of another environment on another celestial body. And it has to do so in at least one way. And I also want to note that many analog environments, or most of them, are natural, but they don't have to be. Analog environments can also be man-made environments here on Earth. And a good example of that is would be a Mars, it would be a Mars chamber. So these are the types of chambers that are built by scientists at places like NASA. And they would build these to be able to replicate all of the conditions we know that exist on Mars. And engineers can use them to put, or to be able to test some of their spacecraft to see how they'll perform when they're actually sent on their missions. So I'm not actually going to talk about man-made analog environments, but I just want you to know that they also exist. So within our solar system, I've put up on the slide here kind of the 3 places we think are the best candidates to search for life. So those are the moons. Oh, and sorry, it looks like the formatting got changed a little bit, but it's Europa and Enceladus, which are the moons of Jupiter and Saturn, and then there's Mars. So what I'm going to do is I'm going to start talking about Europa and Enceladus and compare them to some of the analog environments we have for them here on Earth. And then I'm going to move over and start talking about some of the environments on Mars. So here are some images of Europa and Enceladus. And one of the reasons why we're excited about these 2 moons is because as scientists, we're pretty confident that both of these moons contain liquid water oceans beneath their surface. So these oceans, and hopefully you can see in the diagrams below, are anywhere between 65 to 100 kilometers deep. So that means that there's more water in these oceans or in these moons than all of Earth's oceans combined. But these oceans are really hard to access, and that's because they're encased basically in these thick layers of ice that are between 5 and 15 kilometers deep. So these oceans are not really accessible using today's technology. But when we actually look at these moons, the surface of these moons up close, this is what we see. So on the left, we have an image of the surface of Europa. And what you might be able to tell is that it's not smooth. So when we actually look at it up close, we see that there are all these crevasses and cracks and things like that. And what that means is that the ice surface is not actually static, right? It's constantly moving. So these ice sheets are bumping into each other, they're pulling apart. And this is important because what this means is there's a chance that the water from the oceans below is actually finding a way to get to the surface. So if there is any life or biosignatures within those oceans, it may actually be accessible on the surface. Similarly, we see Enceladus is the same way. So that's the image on the right. It also has a lot of cracks and crevasses and ways for water to get to the surface. But what I hope you can tell in this image is that there are actually these plumes of water that are shooting up from the surface. So what that means is that this water from the ocean below is actually going straight out into space, and eventually it's going to come back down and settle on the surface of that ice. So again, what this means is that we might be able to actually access those oceans underneath, or to learn something about them by studying the ice above. And our lab has just started to do this, and we're trying to think about, okay, where are the best environments on Earth that we can do this type of research? And what we've decided is that is in glaciers and ice sheets. So in the top image, we have White Glacier, which is in the Canadian High Arctic. This is near is actually near the McGill High Arctic Research Station. And then in the bottom image, we have the Devon Island ice cap. So what we've started thinking about is, okay, the questions that we want to try and answer is, can life actually survive in ice? And if it can, what kind of biosignatures can we detect in this ice? So these are 2 images of both, or on the left, these are images of White Glacier. And then on the right is an image of the Devon Island ice cap. And the first thing I want you guys to be able to tell is, looking at the White Glacier, is that, again, it's not very smooth. So just like the surfaces of Europa and Enceladus, but it's also very dirty. It's not like pure ice. It's not pure snow or anything like that. It gets a lot of dirt and debris and mud, which ends up being blown in from the surrounding mountains. And this is important because this dust and debris provides nutrients for the microbes that are also being deposited on this ice. So this provides them a source of energy and potentially a source of carbon for them to utilize to be able to survive here. Now, kind of in opposition to that, we have the Devon Island ice cap, which is on the, I guess that's on the right. And you can see it's a lot cleaner and it's a much more sterile environment. There's a lot less of those nutrients that are being blown in. And we actually see that in the microbial data as well. So there are less microbes in the Devon Island ice cap than there are in White Glacier. Nevertheless, though, and that's the research that I'm doing right now, is to determine if these microbes in the Devon Island ice cap are actually active. Are they metabolically active, and are they actually able to survive here? Because if they can survive there, then it bodes well for looking for it on the surfaces of Europa and Enceladus. And then I'll just show a few more images just because I think it's cool to look at. But this is from our expedition to the Devon Island ice cap this past summer. You can see I'm in the bottom right corner taking an ice core. One of the cores is above that and in the top left. And then I've also put some images here of a drill that's actually being worked on by engineers at Honeybee Robotics. So Honeybee Robotics is an engineering firm in the United States, and they get a lot of NASA contracts, including one to design a drill that they hope will one day actually be able to go to Europa and Enceladus and actually be able to drill through the entire ice cap, through the entire ice surface in a time frame of about 5 years from when it lands. And they love using the Devon Island ice cap as an analog environment for this because the Devon Island ice cap is 800 meters thick, right? So if you're going to do this type of testing, you can't do it in a lab where you might only have a few meters to work with. You really need to be able to test it over very long periods in real world environments. So it's another reason, not just from a life detection standpoint, but from an engineering standpoint of how you can use these analogs on Earth when you're exploring other places in the universe. Okay, so I'm going to start talking about Mars now. And the first environment I'm going to talk about are lava tubes. So lava tubes are a place that I did some of my early research in my grad studies. And lava tubes are essentially a type of cave that forms anywhere on any rocky body where there was volcanic activity. So Mars used to be volcanically active. And sure enough, on the banks of a lot of former Martian volcanoes, we see lava tubes. And a example of one of these is in this image on the left. So this is a large entrance to one of the lava tubes on Mars. And then on the right is a comparison of a collapsed lava tube in Mars and then also on Earth. And I just put that comparison there to show just how similar these cave features actually form. But we need to know why they matter. And scientists think that they may be a good place to look for life. And one of the main reasons for that is because they protect from radiation. So the surface of Mars gets a lot of radiation, which is lethal to all life that we know of here on Earth. Even some types of microbes you might hear about in the news that can survive really high doses of radiation, they won't be able to survive for super long on the surface of Mars, given the radiation that it gets. But lava tubes provide protection from it, right? Because they're underground. One of the other reasons that lava tubes are thought to be a good place to look for life is because we have modeling which suggests on Mars, lava tubes actually accumulate water. And just like in this image in the top right, I hope that you guys can kind of see it, but we have these large deposits of ice. So ice being a source of water that we know all life requires to be able to survive. And then this is the image on the left here is just one I put in just because I think it's really cool. It's probably my favorite fieldwork photo I've ever taken. So this is a lava tube in California. And the surface, you'll see all of that bright kind of sparkly stuff on the ceiling there. Those are all microbial mats. So these are thick microbial mats that are actually reflecting water, which is beating on the surface of them because they're hydrophobic. And I like to look at it and I like to think about it because I think it reminds us that even in such extreme environments like a cave where there's no light and limited nutrients, you can still have extensive biomass and you can have lots of life which is able to survive there and colonize that niche. So, and that's something that we all should be thinking about as we're looking for life on other planets. So next, I'll move on to the second Martian environment, which is cold, salty springs. So cold, salty springs, we know were present in Mars's distant past, but also potentially in its more recent past. And you can basically think of a cold, salty spring as similar to a hot spring on Earth, except for obviously it's not warm, it's cold. And we think that cold, salty springs might have been one of the last habitable environments on the Martian surface. So when Mars was a lot younger, it was a lot warmer and wetter, but as it started to lose its atmosphere and it became colder, and all of the water started to dry up or became frozen away as ice, we think that these springs, which were really salty, would have kept that water liquid and might have been one of the last places for microbes to survive on the surface. So the image on the right it's a pretty pixelated image. It's from, I think, 30 years ago. So the imaging technology we had wasn't as good then, but we think it depicts a dried up former cold, salty spring. So that is actually on the surface of Mars. And I hope that what you can take from these two images is the image on the left is a cold, salty spring from the high Arctic. And I just want you guys to hopefully see that they look similar and they were probably formed similarly as well. So our lab has done a lot of work on that specific salty spring in the high Arctic. So that's Lost Hammer Spring. So most of this work was done by one of our PhD students, Elise Magnuson, who you can see in this photo here. And what she did is she studied the microbial communities in this spring, and this spring is one of the harshest on Earth, and it's one of the coldest. So year round, it's at -5 degrees Celsius, and the salinity is 7 times that of seawater, so about 25% salt, and it has no oxygen whatsoever. And what she found was that despite these harsh conditions, there is an abundant microbial community here which is very active. It's very metabolically active. But these are not your run-of-the-mill microbes that you might find in your backyard. These are chemolithic autotrophs. So basically what that means is they are getting their energy from inorganic gases. So things like hydrogen sulfide and methane and things like that, that obviously if we were put in a room with that stuff, we wouldn't last very long. We'd be on the floor pretty quick. But nevertheless, they're actually living on this stuff. And that's important because these are the gases and the energy sources we know are available on Mars. And these are some of the only ones that are available. So when we think about it, if we were to take these microbes from Lost Hammer Spring, and if we were to transplant them to a cold, salty spring on Mars, maybe a couple billion years ago, they might have been able to survive there. So that's why this kind of result is so exciting. On the right-hand side, I've also included images of the Gypsum Hill Spring, which is also in the Canadian High Arctic, not far from Lost Hammer. And I think it's probably not picking up well on this screen, but in the bottom image, you can see a bunch of microbial mats of a bunch of different colors. And it just shows the diversity of microbes that you can have despite the harsh conditions. And what our lab is doing now, it's an area of active research for us, is to actually study, can these microbial mats preserve biosignatures? And if they can, then it says that maybe that's a place we should be targeting when we search for life on Mars, right? If we go to some of these springs, we might be able to find evidence for past life. Okay, so the last environment I'm going to talk about is actually the Martian surface. So it's actually specifically, I'm going to talk about the regolith, and regolith is basically just Martian soil. And you might be thinking, well, why would you be looking there for life? You already said that the surface of Mars is sterile. And for the most part, we think that's true. But the only reason we know that is by studying analog environments here on Earth, such as the dry valleys of Antarctica, which you can see in this image here. So the dry valleys, as the name suggests, are very dry. They're the driest and the coldest place on Earth. So and people are usually surprised by that because when they hear Antarctica, they think, oh, there must be a lot of snow and a lot of precipitation there. And there is, but specifically in these valleys, there's none. So they are one of the driest places on the entire planet. So we had one of our PhD students, Jackie Gordiel, who's in the top image. She went and did field work in these valleys about 10 years ago, and she took samples from them. And I think this is University Valley on the right. So she actually went to this specific valley. And sure enough, she found basically no life there. So her results suggested that these valleys are actually very uninhabitable to life. And of the few microbes that she did find there, they were basically dormant. They were basically in a form of stasis. They weren't really doing anything. They weren't dead, but they definitely weren't actively growing or doing anything in that environment. They were kind of just waiting, hopefully that one day conditions would get better and they could start to metabolize again. That being said, or despite that, what she decided to do is she went and she took samples of the rocks on kind of the side of the valley. And some of those rocks would be like the one that we see in the bottom image here. And I think it's really not going to pick up in this image, but trust me when I say, when you actually break apart these rocks, just beneath the surface of the rock, you start seeing these layers of different colors. And one of those is actually green, and that's caused by or not necessarily cyanobacteria, but photosynthetic bacteria. Okay, so despite the soil just a few meters to the right of them being uninhabitable, they're actually making a life for themselves in these rocks. So those are called endoliths. And the way they're able to do this is because these rocks are very porous, and the pores actually trap the moisture from the air. So what little moisture is actually in the air gets trapped into these pores, and that's enough water for these microbes to actually be able to survive. So what that tells us is that, yes, the surface of Mars likely is uninhabitable because despite how uninhabitable the dry valleys of Antarctica are, they're nothing compared to the surface of Mars. But it might be something that we should be thinking about and looking at going forward is actually studying or looking for endoliths in the rocks that might be somewhat protected from the harsh surface conditions. So I guess from this talk, what I'm hoping that I was able to give you guys is an appreciation for using Earth's most extreme environments to study life in our universe, right? Before we can really look for life elsewhere, we really need to understand it here and know what its limits are here. So with that, I'll just say thank you for listening. And I think we'll do questions after everybody. Yeah, so I'll take your questions after all the rest of the speakers. Thank you.
So thank you so much, Brady. Everyone, think of your questions. I have so many already, but next we have Sam.
Hi, so my name is Sam McNichol. I'm a PhD student here at McGill in the Department of Earth and Planetary Sciences. And I study microbes that live in our oceans, specifically microbes that live in the sediments deep beneath our oceans. Microbes in our oceans are actually really important for our life here on Earth. And about 50% of the oxygen that we're breathing right now that we need to survive is produced by photosynthetic microbes that live in the surface waters of our oceans. Microbes are important to our life here right now, but they're also really important to the history of our Earth as a whole. And so If you look at the yellow line on that figure over there, you can see that bacteria appear before all these other forms of life, and they actually appeared on Earth about 3.5 billion years ago, whereas we humans only appeared on Earth about 300,000 years ago. So microbes have been really important in shaping our Earth's history and the evolution of the Earth that we live on. As Brady was saying earlier, microbes aren't like humans. They don't just use oxygen to live. They can actually live on a whole bunch of other chemicals. And this is just a list of a lot of the different kinds of things that they can eat and use to live. They can use things that are definitely we can't use, like iron and magnesium, so these metals, and they can also use things like sulfur. A recent study was estimating the distribution of life on Earth by looking at how much carbon is locked up into all these different forms of life. And not so surprisingly, plants make up the biggest biomass distribution on Earth, but bacteria are actually second for the amount of biomass on Earth. And if we dig a little bit deeper into this, we can see down on the bottom for bacteria and archaea that the majority of this microbial biomass is deep beneath the surface of the Earth. So life in the deep can be underneath the continents, but it also can be underneath the ocean. And so there's a marine sediment layer, and that sediment layer is actually pretty thick. And then underneath that, the Earth's crust, which we call the oceanic crust, is underneath the ocean. And you can actually find microbial life living in that ocean crust. So marine sediments, what I study, are really interesting because they can give us insights into both the past, things happening on Earth today, and maybe ways to look for life in the future. And so some of these sediments can tell us about what the ocean conditions or even the atmospheric conditions were like on Earth way back in the past before humans and life as we think of it today existed. In the present, looking at sediments that are deposited now, we can learn about how carbon cycles on our Earth, which is really important for considering climate change and for thinking about how we can mitigate the negative effects of climate change. And we can also use marine sediments to think about how life might have existed on other planets. So life in these subsurface environments isn't like life living here on the surface of Earth. They live kind of at the margins. There's much narrower constraints on things that they need for life, like temperature, pressure, pH. Typically, it's either very cold or very hot in these deep environments. And so they're living like right at the edge of where we believe that life can exist. So my research is, as I said, focused on marine sediments. And we can collect these marine sediments by doing this drilling. And so there's big ships that go out on the ocean, and they have these drilling rigs, which are those like triangular things that stick up out of the top of the ships. And they can actually drill really, really deep down into marine sediments, deep enough to actually reach the Earth's crust that lies beneath the marine sediments. So the sediments that I work with come specifically from an IODP expedition, which is the International Ocean Drilling Project. Expedition 385 is where my samples come from. And a group of researchers sailed out on the JOIDIS Resolution, and they collected some sediment cores that I now use. And to give you an idea of just how long these cores are, on the right is an image of one of those cores after it's come back on the ship. So there are these really, really long cores with a whole bunch of sediment. And we do a whole lot of work with the sediment all the way through the core. So this Expedition 385 was in Guaymas Basin, which is located in the Gulf of California off the coast of Mexico. And Guaymas Basin is really interesting when we're considering like the margins of life, because on the right, you can see where it's spreading center. That's an image showing like the Earth's crust moving apart. And so some of the magma that lies below the Earth's crust is actually able to come up to the bottom of the marine sediments and interact with those marine sediments. And when that interaction is happening, it heats the sediments from below. And so the bottom of the ocean is very cold. It's around 4 degrees Celsius, but in places like Guaymas Basin, we can actually get the sediments really, really hot, over 100 degrees Celsius, 200 degrees Celsius. And so this makes it kind of a model environment to study how life might be living in these really hot environments. And Guaymas Basin is cool, not just deep beneath the sediment, it's also cool at the sediment surface. When this heat is released at the sediment surface, you can get these vents forming, and these can be up to 75 meters or 75 feet high and 33 feet across. So they can be these huge structures. And they form because a lot of chemicals are released when this hot water from sediments down below is released up onto the surface. And it's not just the chemicals that form these structures that's released. There's also things like sulfur and metals, like I was talking about before, that allow microbial life and a lot of diverse life to actually thrive deep below the ocean. And so back to kind of what I do, I'm interested in what energy sources are supporting the microbial life that lives in these hot sediments in Guaymas Basin. And we do that through a lot of lab work, but in a bioreactor, which I don't know how well you can see it, but there's a little clear thing up there, and then here's one where it's filled with sediment. But so I grow microbes in that bioreactor, and I feed them sediment from these cores that were collected in Guaymas Basin. And these microbes, when they eat the compounds in the sediment, they release CO2, and we're actually able to capture that CO2 and then analyze that CO2 to figure out exactly what kinds of things the microbes are eating in that environment. And this work is important for figuring out what kinds of things to look for and what kinds of metabolisms to look for when we think about looking for life on other planets.
Thank you so much, Sam. So last but not least, before our question period, we have the last talk of tonight. Hi, Erin.
Hello. Hi, everybody. My name's Erin Gibbons. I didn't put my name on my slides, but my name's Erin. And so we're going to take a step away from Earth now, all the way to Mars. So I'm a PhD student, also in the Earth and Planetary Science department like Sam, but I'm much more on the planetary science side. So my research is around the possibility of life having evolved on Mars, and then how we can look for evidence of life on Mars today. So I'm a mission scientist on the NASA rover mission Perseverance that is currently driving around on the surface of Mars right now. I got to drive and operate the rover earlier this afternoon. So my main job is what you can see on this little GIF. Perseverance is turning around to look at its little helicopter partner, and the black circle that looks like an eyeball, like a cyclops eye, that's actually a laser that we shoot at rocks, and that's the instrument that I get to help operate. So today what I want to do is just give you kind of a update on what Perseverance has been doing on the surface of Mars, because its prime mission is to search for signs of life that are on the surface using some of the techniques that Sam and Brady have been talking about, and using some of that information. So we're doing an active fossil detection mission with this rover. So I wanted to provide a summary, some updates, and some of the rationale for why we're doing these questions, because we're looking for life on Mars because it would have pretty staggering implications for the possibility to find life on other planets if we find it on our own planetary neighbor. And because of the age of the rocks on Mars, it might actually tell us about our own origin of life here on Earth. Okay, sorry, the slides don't move on the computer. So for the past 2 years, Perseverance has been driving on the Martian surface in a place called Jezero Crater. So this is a depression in the Martian surface that was carved out about 4 billion years ago when a massive asteroid struck the surface and excavated this large hole in the surface. The crater is about 45 kilometers across, so it's quite large, and it's very distinctive from orbit because it forms almost this perfect circular shape. And it's this structure, this very large diameter and this circular kind of bowl shape that got us so excited about this feature, because it's a topographic low, and that bowl shape meant that about 3.74 billion years ago, it collected a bunch of water. So you can see there's a small little curly Q coming in from the left side of that image. So that's an ancient river valley that carved out of the bedrock, and it filled up this crater with water. So we suspect that this crater was once home to a lake, quite a deep lake, a very extensive lake that lasted for several years. So this is a great environment to look for some of these signs of life, because we know from lakes on Earth, they're often very productive environments, lots of biodiversity. And importantly, in lake environments on Earth, when those organisms living in the water, they die, they sink to the bottom, and then they get buried in sediments like clays and silts and sands, and it essentially entombs all of those microbes at the bottom of that lake, preserving them as fossils for scientists to come around and look for. And so that's exactly what we're doing with our rover.
May I ask, you're going too fast for me here.
Okay,
You're talking about the possibility of biological creatures in this lake on Mars.
yeah, so this lake was existing on Mars about 3.7 billion years ago. So the climate has since changed on Mars, and that lake has dried up. So all that's left behind is the dried rocks that used to exist on that lake bed. And that's what we're exploring with the rover today. And we're exploring those rocks to look for fossils of life that might have lived in this lake. So it's a hypothesis. But we selected this location because we think it's one of the best places on Mars that life might have existed. We don't know for sure, it's a hypothesis, but we think it's one of the best places to look for these fossils. And that's why we've sent our rover to go excavate some of these rocks and look for the fossils that might have been buried there. So we've kitted out our rover with a ton of instruments just to answer this kind of question. So we have 23 cameras on board. We have a subsurface radar instrument that can tell us the structure of these lake sediments beneath our rover. And we also have several spectrometers that study the chemistry and the mineralogy of the rocks that make up this ancient lake bed. And the chemistry and the mineralogy, that tells us the conditions of this lake. So that can give us hints about how warm the lake was, what the temperature was, how acidic it was, what kind of minerals were forming. And that's going to give us an indication of what kind of life could have lived there if it ever evolved. But most importantly, what the Perseverance rover carries is 43 sterile titanium tubes that are capable of holding about a finger-sized piece of rock. So it's a small amount of rock, but it's a finger-sized piece of Mars that we can extract from the surface using a drill that we have on the rover. And so this is an example of what some of those drill holes look like on the surface of Mars after we've extracted a sample. And so far throughout the mission, you can notice that we've been taking 2 samples of every rock that we deem kind of scientifically exciting and interesting and worthy of a sample. It's pretty expensive energetically and power-wise for our rover to take these samples. So we're very judicious about the samples that we're selecting. But so far, we've been taking 2 samples each time, and I'll get back to that in just a moment. But kind of the wild or interesting thing about this mission is Perseverance as a rover itself is not able to answer the questions of this mission. Perseverance is not able to search for signs of life in a very conclusive manner. And so what we have to do is we have to bring these samples back to Earth so that we can give them to researchers like Brady and like Sam, who have really incredible lab equipment to look for the fossils that may be preserved here. And so that means these samples have to come back to Earth, because if we want to do our due diligence in searching for life on Mars, we need to bring these samples to the best laboratories, the best scientists, and the best instruments. And that's all here on Earth. It's like Brady mentioned at the very beginning, we have to really make sacrifices when we send instruments on spacecraft to other worlds, because they have to be light, they have to be efficient, and they have to be able to survive this multi-month transit to another world. So we're not sending our most sensitive instruments to Mars. And so to look for life, we want to bring those samples back to Earth where we have those sensitive instruments. And so that process has already begun. So this past month, so the month of December and kind of turning into January, the Perseverance rover has been spending all of its time dropping off some of these sample tubes full of Martian core back onto the surface of Mars. And remember when I mentioned that we've been taking so far 2 drill cores of every sample we think is exciting? We've now been dropping off exactly 1/2 of them on the Martian surface. And this is our backup sample cache. The Perseverance rover is still holding on to the other half of those samples, and that is our main sample cache. That's the one we're most excited about, but we're leaving behind a pair of samples as backups. Again, we'll get back to that. But the next step is to actually bring these samples back to Earth. And this is where it gets complicated, because we've never launched a rover from Mars before. So this is all, it's a plan. Sorry, I put a GIF. So this is what it looks like when we drop a tube on Mars. You can see the excited little engineer. And then this is a photograph of what we've been doing for the past month and a half. So there's one of our sample tubes. That's a real photo sitting on the surface of Mars, waiting to come home to Earth. And the way that we're going to do that is in 2028, ideally, a spacecraft will take off from Earth, arrive to Mars in 2031, and this is the Mars Sample Retrieval Lander. And the plan is Perseverance as a rover will drive over to the Mars Sample Retrieval Lander and give it her samples. The Mars Sample Retrieval Lander will retrieve the samples and then transfer them to a rocket that is stored inside of the lander itself. Now, in the case that Perseverance meets some tragic end in the next few months or years, and she cannot drive her samples over to the retrieval lander, the lander is going to be equipped with 2 small helicopters, drones, and they will fly over the Martian surface and they will pick up those little tubes that we left behind as little breadcrumbs. So this is why we have a backup cache on the surface, but Perseverance is expected to drive her samples over to this retrieval lander. The retrieval lander, like I said, will transfer the samples into a rocket, which will then be ejected out of the lander, fire its thrusters, and launch itself into the Martian orbit. Again, this technology doesn't exist yet. This is the plan. All right, so once we have our Mars ascent vehicle in Martian orbit, it's going to rendezvous with a satellite that has been orbiting Mars for about 5 years at this point. So it's going to toss the samples that it's holding over to this orbiter. The orbiter is going to catch them. It's going to fire its own thrusters and fire itself back to Earth. Now, this orbiter is never actually going to make it to Earth. It's going to go on a trajectory that has it land in the sun. But on its way to the sun, as it passes Earth, it's going to throw the samples at Earth. I didn't come up with it. This is just my job. So as we go by Earth, we're gonna throw the samples. They're going to enter Earth's orbit, and they're going to crash land without a parachute into the Utah desert. And then the science begins. Then we get the samples and we start distributing them out to other scientists. And we start looking for signs of life. But okay, so this sounds like science fiction. It's not. This is the real official NASA plan. And we're putting all of this, so we're inventing rockets to fire themselves off the surface of Mars, rendezvous, get to Earth, land into the sun. And we're doing this because we really want these samples back on Earth. It is not enough for us to send robots to Mars, as sophisticated as they are. We will not get a definitive answer of whether there's life on Mars just using robotic explorers. We need to bring these samples back to Earth, where we have high quality instrumentation and high quality labs and high quality scientists. So that's why. And this is because the fossils that we're expecting to find on Mars, they are not the bones and plant fossils. They are not the well-preserved fossils that we find on Earth that give us unambiguous, definitive evidence that Earth has been inhabited by life for a long time. Mars is a much more harsh environment. It's like those analog environments Brady was telling us about. Only we don't know what kind of life lived on Mars, but we hypothesize it was probably very small, primitive. If it ever evolved, it would have probably never gone past the point of a microbial system. So we are looking for very small fossils you cannot see with your naked eye, probably chemical fossils that you have to extract. We don't have that instrumentation on our rovers. We don't know how to put it on a rover. We don't know how to miniaturize it. So we want to bring these samples home to look for these fossils. The other aspect is we want to be able to do repeated analyses. Again, these rovers just don't have the capacity to do the kind of high resolution science to answer these questions with such a big scope. We're trying to see if there is any life beyond Earth. We need to do our due diligence. We need to do repeated analyses. And so one example of what happens when we don't have that kind of due diligence built in is there was the kind of science scandal back in the 90s. The Allen Hills meteorite, which is the top image there, it's a Martian meteorite. It was found in the Antarctic. And some researchers were investigating it, and they found what looked like microbial fossils preserved in this meteorite. And they thought it was a definitive sign that we have fossils on a Martian meteorite, there's life on Mars. A couple other scientists relooked at the samples. They did high resolution analysis, like we want to be able to do, repeated studies, and they found that's probably just a weird shape of a mineral. It was not life found in this Martian meteorite, but it really kind of left a bad taste in the public's mouth. They got excited about this possibility of life on another world. Scientists then retracted their original claim. It started some distrust. So we really want to avoid that. We want to do the science. We want to answer these questions right this time. We want to bring these samples home, analyze them several times with very good quality instruments. And that's why we need to bring our samples home. That's why we're spending so much time searching for Mars and architecting this insane mission to get those samples home. So that's the Mars 2020 Perseverance mission. It's ongoing. We're still working on it. So if you have any questions about the mission or Mars sample return, happy to answer.
All right. So thank you so much to all of our speakers. I'll invite all of you to come up to answer any questions we have. And I already see that there's one at the back. So yeah.
How can these samples go through this atmosphere without a parachute and not?
Well, that's such a good question. So MDA is the one who is engineering the capsule that will take these samples from orbit and into the Utah desert. They're using right now, they're testing it at the moment. It's a lightweight composite material that has a very good thermal resistance, so it doesn't get hot as it's firing through the atmosphere. And it's so hard that they've been doing hypervelocity impact tests with it right now, and not a single one of their tests has cracked. So far, all of the technology that they've tested is indicating that even if you're dropping a spacecraft from orbit, they have the technology to keep it sealed and intact. So, and I forget why they didn't put a parachute on it. It's been a contentious point in the community, but the NASA engineers are firm that there will not be a parachute.
And that's the follow-up. So what about the samples themselves, right? Because the canister doesn't crack, but the samples presumably are still being subjected to those really high G forces. So is there any worry that the samples themselves will be altered in any way, either, you know, they're squished together or whatever, and we'll lose information from them?
Yeah. So there was a big planetary science meeting last year in Athens. A lot of the world's planetary scientists got together and we talked about this issue, and it was probably one of my favorite science moments. It was like a legitimate heated discussion among scientists in the room. People were standing up, people were yelling. Because some of the things that we're interested in these samples is we want that fine resolution layering. We want to be able to drill into these rocks and look at how they're constructed. And so if you're shaking the sample on a re-entry trajectory, you're going to shake up, you're going to move those grains, you might fracture the rock. So currently we don't have an answer to that kind of question. The samples will right now probably be damaged on re-entry, but we have until 2028 to figure this out. So yeah, so figure it out. So it's an ongoing question. Yes.
I was wondering about the timeline of basically these experiments in Mars, because it's harsh environments. What does it look like in terms of like one person's career? Because sometimes you don't even know just the end of a certain experiment because it's taking so long. How do you kind of deal with that?
I mean, so yeah, so that is a challenge for sure. Like one of the big ones, and even some research that we've been doing in our lab, is trying to understand what happens to DNA as it spends time on the Martian surface. So can we detect DNA even after it's been exposed for a long time on Mars, because we hope to one day be able to send maybe a DNA sequencer on a rover to Mars. But that's one of those things, right, where there's no way for us to be able to simulate perfectly DNA being exposed to Martian conditions for, the hundreds to billions of years that it would have been there, since maybe there was actually an active microbial ecosystem there. So one of the ways we can get around this in that specific example is by increasing the radiation dose, right? So if we're worried about or if we're trying to simulate how radiation affects DNA on the surface of Mars, rather than a kind of lower amount of radiation over a longer period of time, we can crank up that dose. So it's the equivalent, but only in, let's say, a few months rather than, hundreds of millions of years. So that's one way that you can kind of get around it. But for sure, it's a massive challenge to be able to study processes on kind of these geological timescales.
Yeah, I guess for the work that I do, so the organisms that live actually in the sediments that deep down where my samples come from grow incredibly slowly, and people that actually grow them in the lab, like grow them under the same pressure and the same temperature. They do these experiments for like 60 days, 120 days, so they take a really long time. And the way that I'm getting around that is I'm using things that grow on like the time cycle of days to weeks. And so they're not what's actually living there, but they do still eat the things that we're looking for in the sediment. And so we can get around that by like using things that I can actually observe in a reasonable amount of time, and that can still give us valuable information without having to wait so long.
Yeah.
How did you drive the Mars rover?
From my office. Okay. During the pandemic, it was from my bedroom. It's a really great collaborative program. So there's just NASA has a couple. They've set up sectors so that you can have international collaboration, because the bulk of the team is in California. About half of my team is in France. We've got another constituent out in Spain, and then I'm here at McGill. So we have a way of logging into the NASA computer. So we have a VPN. We tell our computer to pretend it's at NASA, and then we can access all of the tools that they have there. There's a lot of like verification. I have to prove that I am me, and like only I can access that data. But so there's a fair bit of security, but it's just, we just log into a tunnel, and then we all sit on like a Zoom meeting. Everybody who's on the mission that day, we're on a Zoom meeting. We talk about what we want the rover to do. Everybody kind of goes off their own and codes up what they want the rover to do, and then we just discuss throughout the day. So it's everyday operation. It's just sometimes your staff. And, yeah. So it's just,
Yes, there's someone in the back earlier.
I take it there's a general agreement about the definition of life. What life is there is something common to all forms of life on this planet. Would that be right? I've seen diagrams which show that even though there's an enormous diversity, there is a common element to life on the planet. Is that agreed?
yeah. So there's a concept of what's called the last universal common ancestor.
Sorry, I didn't catch that.
It's called the last universal common ancestor.
Good.
And the idea is that every organism that is currently living on the planet, you can trace its lineage through the billions of years that life has existed here to one common ancestral organism, so a single origin of life. So we don't necessarily know how to define exactly what it is to be alive, but we do know that all life on Earth is related.
That's what I understood, yes. So we're into a situation where there's a possibility of examining a form of life that has evolved on entirely independently. And so I wonder whether people ask questions about whether there are other possible ways of looking at life on this planet as possible models for alternative kinds of life on different planets. Have people thought about that
Yeah.
possibility?
Yeah, so a couple thoughts on that. There's a couple ways that we approach searching for life on other planets. One is we only know what we know. So we know what life on Earth looks like. It's carbon-based, it uses water. So it's easier to look for that kind of life. We don't know how to look for a life form that we've never encountered before. Maybe we'll do that in the future, but we don't even know how to design those experiments. So we're starting with what we know. So yes, right now we're looking on Mars for life that's like life on Earth. And that's not unreasonable, because the basic biochemistry and physical laws that have created the kind of biology that we have on this planet, it's fundamental and it's basic, and it probably exists on Mars too. You have an abundance of carbon, you had water, those bonds and those reactions still work the same. So we suspect a similar biochemistry to be common. But yes, there's several labs that are looking into maybe silicon-based life forms or other ways that life could make a living that we haven't seen before. I don't know if you want to expand it.
No, I was basically going to say the same thing. So synthetic biology is an active area of science and of research. So there are labs around the world that are doing synthetic biology and trying to create different forms of life. So like Aaron said, life that is where the DNA is actually based on silicone rather than carbon. There is a major controversy about, I think a decade ago, where some NASA scientists claimed that they found life on Earth that was that used arsenic in its DNA molecule, which turned out to be not true at all. But again, it was this idea that can we look for life that is not based on what it is here on Earth. But like Aaron said, it's really difficult to do because it's almost one of those things like where we don't have the imagination yet to really think of what it could be, because we're so used to just knowing what we know, which is what's here on Earth.
Yes.
This is a very simple question. Maybe 20 odd years ago, when we were much earlier in this whole process, I remember the scientists were talking about Titan as being one of the highest possibilities of life in the solar system. Titan seems to have fallen off the map. What did we discover? No. Okay.
Oh, no, Titan, sorry, Titan is not off the map. There's such a cool mission about to go to Titan. It's called Dragonfly and it flies. So it's like, I'm really excited about it. It's a quadcopter. So it has 4 like helicopter rotors and it's going to leapfrog along Titan because Titan as a world, it's so far out in the solar system that it has continents made of ice, but they're harder than the rock on Earth. And it has lakes and seas, but it's so cold and the pressure is high that there's seas made out of methane and ethane. So gases on Earth are condensed into oceans and lakes on Titan. So the spacecraft is going to hop and fly from icy continent to icy continent, and it's going to look at this weird chemistry. And so, yeah, that's coming up in the next decade or so.
And I didn't mean to, well, actually, so I had a picture of Titan in my talk and I removed it actually and decided not to talk about it, not because I hate Titan, but because, and Aaron kind of already talked about it, a lot of the environments on Titan are ones that you can already kind of find on Europa and Enceladus or on Mars. So I thought, well, it's kind of a combination of those other ones, so I'll just focus on the others. But not only do the environments exist on Titan that Aaron said, but we think it may also have a subsurface ocean beneath that thick ice. So you've got an active hydrological cycle based on methane and ethane on the surface, and then you might actually have liquid water underneath the ice as well, which so Titan is a crazy place. And yeah, we're really excited about the Dragonfly mission that's going in a few years.
Yeah, not forgotten.
Yes.
I just want to thank all 3 of you for the really interesting talk. And I'm just going to ask sort of a general question about this field and opinions. So for example, if you discover like a really interesting microbe that's able to survive like super harsh conditions, are there certain groups that would be like, okay, let's see if it would be able to survive on Mars, or other groups that would be like, no, let's try to retain this as much as to its like original endogenous location? Is there any like sort of, I don't know, ethical thinking behind that, or is it more like field to damage?
Do you mean like actually if we found the microbe actually like take it to
Yeah,
Mars?
like take it somewhere or see if there's like, you found something in like a salty spring, see if it would also survive in like the dry Antarctica.
You might be able to comment on this a bit, but so there would be no plans to take a microbe and actually try and put it in, let's say, the Martian regolith, for example, or in an old Martian spring. And that's due to something called planetary protection. So NASA, as well as, well, basically most of the, I think, well, a lot of countries on Earth have signed the NASA or the planetary protection laws, which basically prevent that from happening. So they protect both from contaminating another world with kind of Earth microbes and things, and it also protects Earth from being potentially contaminated by things coming from another planet. So for example, the spacecraft like Perseverance that Aaron works with has to be extensively sterilized and cleaned before it can actually be sent to Mars, and that's to prevent any microbes basically hitchhiking a rod there and potentially contaminating the surface. Because obviously, if we do find life on Mars, we don't want to have just rediscovered Earth life, right?
Yes, go ahead.
How deep do these core probes go? So how far down is it shielded from radiation?
On Perseverance?
Hmm?
On Perseverance?
Yeah.
About 7 centimeters. So they're small little cores. We're not getting deep. There is a mission proposed by Europe that would drill about 2 meters into the surface. It's on hold because of the Russian-Ukraine war.
Actually,
It might not be.
2028 is when that mission is
Okay.
going now. They've announced it, but yeah.
It was supposed to fly 2022, but it didn't. So yes, we are hoping to get deeper with other missions. Right now, Perseverance is only sampling the surface, but that's also different objectives. So Perseverance is explicitly looking for fossil life. We're not looking for anything living today, whereas ExoMars does have a goal of looking for life that might be alive today. So they want to dig deeper to where it could be protected from the harsh surface. but we're just looking for fossils, and so they could potentially still be in that top surface.
There was you at the back, yes. In the gray, yeah.
In 2020, there was some news about gases that were found in higher layers of the Venusian atmosphere on Venus that could indicate life. What happened with that? Or was it just like completely non-conclusive? It's like, oh, gas, okay. Cool.
No, it's still being investigated. So the gas you're talking about is phosphine. It's so on Earth, phosphine is almost exclusively produced by microbial activity. So when they found it in the atmosphere of Venus, the initial conclusion was that there was not a very good explanation for how that phosphine could have got there unless you had a biological source. There were other research groups that reanalyzed the data and either did not find the phosphine signal or could come up with models that could produce phosphine just from geological activity. So right now it's an open question. There's still a large number of people in the scientific community who do think it's a biosignature, and several other people who contest that. There is a private mission funded by a scientist at MIT, I believe. So it's not affiliated with any of the national space agencies, but she is funding a mission via public funding to go to Venus and sample the phosphine. So it's
the only thing I would add to that is actually from the microbiologist standpoint is phosphine is found on Earth close to life, but we have no evidence to suggest that life is actually producing it. So we seem to only find it with life, but we have no scientific basis to understand why it would, because it seemed like, okay, it's being used for energy metabolism, but then the phosphine is made up of phosphorus, and phosphorus is one of the most essential nutrients for life on Earth. So it doesn't make sense that you'd be giving it away, right? You'd be making it into a gas and giving it away, right? Because it's so essential to actually just incorporating into your cells. So scientists, we see it with life, but but we have no understanding or we have no evidence to suggest that life produces it. And therefore it's kind of contentious about like, is it actually a biosignature, whether it is on Venus or not, which, as Aaron said, is also a huge debate right now.
Yes.
The lake Mars that we were talking about, you said that it was liquid for about 300 million years, I think. So if we scale that to the speed at which microbes evolved on Earth, do we think that it could have gone through multicellular life into like cyanobacteria or something like that? Or do we think only unicellular life?
So with Jezero specifically, I didn't actually put an age range on how long the liquid water was there because we don't know for Jezero. For Mars as a whole planet, we have some estimates of a couple million years of water. It varies kind of each year as we learn more about Mars, but it's potentially that it was wet for about 1 billion years at the beginning. That being said, the water was not always connected. So you often had just these, it wasn't a very, we don't really know. The general consensus is it wasn't a continuously wet world in the way that we have like oceans on our planet. So it might have been wet in pockets. And the problem with that is that would really limit the amount of kind of exchange between some of these microbial communities and limit how much they could evolve because they're not necessarily interacting with other communities. They're not being forced to drive the evolution. The other thing is Mars is much further away from the sun. There's been some modeling efforts that suggest photosynthesis wouldn't even really be a viable option to develop energy on the surface of Mars. Again, that's also contentious. But the general take of Mars is that it never would have gotten to the point of complex multicellular organisms with differentiated tissue. So you're not talking about any bones. Whether we reach photosynthesis, that kind of splits the community, but staying as a single cellular life is generally accepted. So we're looking for very simple life forms.
So we have a question online that says, what are your thoughts regarding the concept of panspermia? And can you explain what that is, I guess?
So panspermia is basically the idea that if there is life on Mars, basically it shares a common ancestor with life on Earth. So you might have had it earlier in both of the planet's history. You might have had, let's say, an asteroid that smacked into Earth or something, and and a part of Earth broke off and eventually made its way to Mars, and it seeded Mars with microbial life, or vice versa, essentially. So one common ancestor, and that is it's going to be hard to tease that apart. If we find life on Mars, to be able to determine, if it does seem like it's similar to life on Earth, is that because of panspermia, or is that because of contamination? And one of the ways to look at that is to make phylogenetic trees. So those are kind of like, you might have seen them in grade school, how you have how all life on Earth is connected, and that kind of creates a tree. And we have computer models where you can use DNA and you can actually create these trees. So one way might be to use that, right? So you can see, okay, they're related, but how far back was their most common ancestor? Was it 4 billion years ago that was their most common ancestor, or is it something more recent, which might explain contamination? But even that being said, it's very difficult to prove, which is it, contamination or panspermia. But it's a legitimate scientific hypothesis, and if we do find life on Mars or somewhere else, it's up for debate how likely that would be.
So I was wondering, for analog environments or for like samples from like the deep surface, if it's only recreating certain conditions of like areas where we're trying to see if there's potentially life, how accurate is the data to predict if life can develop on like the different moons or like planets?
I guess we don't really know how accurate it is. For the stuff that I look at, I guess that it's more like, so it's kind of like right on the edge of where we think it's possible for life to exist, right? Or potentially like there's some sediments that are so high temperature that there is no life at all, as far as we know. And so it's like, for my stuff, it's asking the question of what would a single-celled organism have to look like to be able to live in something like that, like something like Mars. And so it's more of like, can we find an environment here on Earth where we can hypothesize the kinds of things to look for life?
I think some of the value that analog research has given us is also, it's just expanded our understanding of what life can actually survive. So early in the days of astrobiology, there was a lot of hypotheses that there were certain places on Earth just were uninhabitable. They didn't think you could live in volcanoes or in hot springs or up in the Arctic. It was just because they were conditions of life that you don't see organisms living in. But then we started looking at microorganisms, and you find we've expanded the temperature range that we know life can survive by 10s, 20s of degrees and or down. And like, we find life living at a pH of 0, which is so acidic it's off the scale. And so by studying these analog and extreme environments, we've just expanded the envelope of what life can actually survive. And so we know it's not unreasonable to look at other worlds that maybe at first glance, they look uninhabitable. They're covered in radiation, they're dry, they have no water, it's hot. But we've got that on Earth and we've got life there. So it's at least expanded kind of our capacity to hypothesize.
And we can't forget too that if life arose independently on another planet or another world, it would have also gone through evolution as well. So, right, life has evolved to the condition, like life on Earth has evolved to the conditions present on Earth. There's no reason for life on Earth to have evolved ways to survive for long periods of between -60 and -120 degrees Celsius, like you find on Mars. But given that selective pressure, evolution may have actually found a way to do that. But of course, we wouldn't expect to find that on Earth because there is no selective pressure for that.
Questions? I have a question if people are still thinking. Okay, yes, the question.
So, you were saying like there's some planetary agreement not to bring microbes from here if they'll survive on Mars, but then you were saying that there's a mission to find living organisms outside of Earth. So those are going to be brought back to Earth, I'm assuming, to find them.
Ideally not.
So,
Yeah.
so comment, or to ask, the rover doesn't have the sensing equipment, so you send the drill samples back here for the data. So does that other mission have real sensing equipment on it to analyze stuff in kind of real time?
So I don't know the full instrument suite on that mission. I think it does, maybe I would.
So, it's not that we can't bring samples back to Earth that may have microbes in them, but we just have to be really careful. And it also means, like, for example, there are certain areas of Mars, as an example, that are off limits right now. We're not allowed to go explore them unless we sterilize our spacecraft sufficiently. And there are certain guidelines on how sterile they have to be able to go there. In the same way, bringing samples back, there needs to be plans in place that you're not exposing anybody to any dangers. You know, it's more, to me, it's more sci-fi that people are worried that, you know, a Martian pathogen is going to kill all life on Earth. I think that's more science fiction than anything else, but nevertheless, it's something people are thinking about. So when the samples that Aaron was talking about that are brought back to Earth, they will actually be going straight into a level 4 lab. So a level 4 lab are the type of labs that you would have, like you would do like studies of Ebola or coronavirus and those types of things. So super high containment, so that if there is anything in them, it won't get out and contaminate the rest of the planet.
And those facilities are being built now, even though we're not expecting the samples to come back for at least another decade. So we have about a decade of technology innovation built into that sample curation process.
So I was curious about how you validate your data in terms of metabolic activity. Like, how do you say that it's the metabolic activity is present and absent? Like, what kind of controls do you use for this?
Yeah, so controls are super important. Maybe you can figure it out in the active experiment. But controls, so negative controls are super important. It kind of depends on how you're wanting to, like what you're wanting to use as a proxy for metabolic activity. There's a few different ways. So there are things like where you can do active experiments using radio labeled carbon. So the microbes, if they're active, they're going to take up that carbon, which is radio labeled. They're going to respire it into CO2, and then you can measure the radioactivity in the gas. There's other ways, like some of the methods I'm working with is you're actually looking for RNA. So we've talked a little bit about DNA. RNA is another kind of nucleic acid that all life has. And it is only produced by microbes that are metabolically active. So it's not a direct measure of metabolic activity, but you know, if you see RNA in your sample, you know, it could have only been produced by a living, breathing, active microbe. And basically, you know, like you said, controls are really important. So to make sure that we're validating that it is in fact true, we're comparing it to a sample that we know either we've killed it, so we know that there can't be any living microbes, or we've gotten rid of all of those microbes. And you compare them that way. I don't know if you have.
Yeah, so in the things that I do, we sterilize all the sediment first. So like we kill everything in it, and then I introduce something else there. And so I'm looking at CO2, and basically if there's no CO2 release, then nothing is growing, because they're not eating any of it, they're not producing anything. But people that do experiments with the microbial community that actually lives in these sediments, they'll have controls where they sterilize the sediment. And so they like do the exact same kind of incubation at the temperature and pressure, and they let it go for a really long time. And if they don't see any growth, then they know that they successfully killed everything.
In terms of your experience with microbes, except of the metabolism of using iron or sulfur or whatever, what exactly are the ways that these microbes, in terms of proteins or lipids and so on, adapted?
I look at microbes that eat hydrocarbons, so like long chains of carbon and hydrogen, like fats and things like that, but they're definitely in the sediment. And one of the big things in the marine sediments is the use of extracellular enzymes. So there's organisms that can actually release enzymes that degrade these larger compounds into smaller things. that they can actually like, take up into their cells and eat. So that's like one of the big things that I'm looking at is whether there are organisms that are able to break down these really large compounds, because in these sediments that get heated, they tend to, you can actually produce oil deep below the ocean. And so you like conglomerate a lot of these compounds into these big things that are mostly inaccessible to a lot of microbial life. And so we're looking at whether things can release things externally from themselves into the environment to actually like break it down into something that they can then eat.
I think we have time for one more question, but we'll also stick around a little bit if you want to come down and ask. Okay, two more. There are two more questions. So we'll go with
You
you.
said that there was the need to get definitive evidence in sample return from Mars. Is there convincing like ambiguous evidence that there's life there and we just don't want to be embarrassed again, like you said before, or like because I remember seeing these blueberries that they found on Mars and there was big talk about that, and so yeah, is there good evidence that there's life there?
Challenging me as a scientist. There's a lot of contextual evidence that lends us to the belief that life could have lived there. So the other thing is Perseverance is the final, not the final, but the latest iteration of a long series of missions. And so the Curiosity rover, which is the Perseverance predecessor, still active, but it's been on Mars for about 12 years now. Its whole mission was just to understand if Mars has even ever had a habitable surface that we understand. Could life have ever lived on Mars as we understand life to be? And so what Curiosity found was evidence of water, evidence of carbon compounds, evidence of nitrogen, phosphorus, sulfur. All of these compounds that we know life needs are present on Mars in concentrations that life could use. So once we establish that baseline, okay, theoretically life can live on this planet. And we're also seeing carbon compounds. So we don't necessarily have the technology on a rover to fully understand what these carbon compounds are. They're consistent with the kind of carbon compounds that life uses, but again, we need to bring them to Earth to really figure out what they are and whether it's, because you can produce carbon compounds with life, and you can also produce carbon compounds with geology. So we need that higher resolution analysis to look. But so kind of more precisely answer your question, we've established that Mars is habitable. It had all the conditions we understand it for life to have emerged, and we just want to answer that final bit of the question of, did it? And part of that question is we don't really know what sparked life on Earth. So even if we find out that Mars is uninhabited, but had all the conditions for life to emerge, that's kind of cool. Because then we have some more information about what could have sparked life here and what was different on Mars. So either answer is quite cool. But yes, we've established a baseline. We would just wrap that final bit.
And I'll just add quickly, the first mission to ever look for life outside of Earth was the Viking missions that went to Mars in the mid 70s, and they actually contained a biology package. So there was four experiments within this package that were designed to look for life, and this was kind of the first contentious evidence. But it goes to what you were saying or asking about ambiguous signs of life. So basically, one of those four experiments had a signal that looked like it should be life, but the other three had a negative signal. So the scientific community came together and they said, well, all these results taken together seems to suggest that, okay, there must have been something wonky with that one experiment because the other three are saying the opposite, right? But that's one of those ambiguous signs of life that we had, and that was kind of the first major debate for life on Mars. Since then, we've learned a lot more about Mars, but it just goes to show, and it gets to the point that we can never determine life on Mars or another planet with just one method. There has to be multiple methods in agreement. For a really great claim like that, there has to be really strong evidence. And scientists talk about this all the time. It has to be from more than one kind of source, which is why sample return is so important, because you'll be able to do all of these different tests and different types of analyses. So if one of them shows up as, look, there's life here, we can then give that sample to all of these other people doing all these different methods who can hopefully corroborate it, so that we get that unambiguous kind of sign of life.
There's one last question over here.
Just a quick question, on the Perseverance mission. What criteria select a rock as interesting enough to sample?
Oh, that's such a good question. So one, there's a couple logistical constraints. So we need a rock surface that is at least, I think, 14 centimeters across and flat for our drill to even be able to contact and stabilize itself. So that's one constraint. So we can't do any small rocks. In terms of what makes them interesting is we're looking for either environments that we suspect to be habitable. So we look at a rock and we think, okay, this has all of the conditions to preserve fossils. So for that kind of condition, we're looking for things like sedimentary rocks. So again, this is the kind of rock that would, the sediments at the bottom of the lake, when they eventually harden into a rock, that's called a sedimentary rock. So we find that kind of rock type, we know, okay, this formed in contact with water. Potentially there was organic matter raining down into it that it's preserved. So those types of rocks we would definitely sample. The other type of rock that we are interested in are igneous volcanic rocks, and we're not sampling them for biological samples. We don't think igneous rocks really preserve any fossils, but you can date the crystals in there really, really well. And right now, we don't really know how old the surface of Mars is. We can estimate, and we've got decent estimates and parameters, but we don't really know. And so it would really help if we knew how old Mars was and also be able to relate that to how old we know life on Earth is and just understand whether this place was habitable at the time that Earth was inhabited. So we're collecting samples that are either interesting for understanding the environment and the age and history of Mars, and also samples that we suspect from all of those other instruments on our rover, our cameras, our spectrometers, the chemistry, the mineralogy. If those things reveal collective evidence that this rock probably formed underwater in an environment that we know could support life, we're going to sample that rock. But we also only have 43 tubes. So we're trying to save some for all the cool rocks we expect to see later. So there's been a lot of debates on the team. We're expecting pretty cool rocks to be encountered in the next year or two. So we've definitely saved about half of our tubes.
All right, so I think we'll end the question period, but we'll stick around for a few more minutes if you have some other questions that you want to come up and ask. Before we go, let's thank our speakers one more time. Thank you so much. Great talk. Last but not least, we have our winners of the raffle. So if you are Luz, Gioti, or Miranda, please come see me. Are you all here? Yes. Are you all here? Because otherwise I'll pick someone else. Okay, if everyone's here, please come see me. And last, we do this. We have public talks on various topics in space science the last Wednesday of every single month. So these are the dates for the next few months. We hope to see you there. Again, we'll stick around for some questions, and thank you all for coming, especially in this storm. So thanks, everyone.